Okay, so we're going to continue our kind of basic development of graph theory here with the introduction of some standard graphs, a little bit of standard terminology, and then our first theorem, which is a very gentle one. So there's lots of freedom in making graphs. There are lots and lots of graphs on n vertices as n gets large, but there are some that really deserve a name because we'll be coming back to them again and again, and I want to give names to 4 basic ones here. So this is going to be all about standard graphs. For the start of today's lesson. The first in this list is the null graph. This is the graph, the unique graph that has no edges and no vertices. So the edge set and vertex set is empty. Now, this is a graph, but unfortunately, it's sometimes an exception to theorems that we care about, and so we are generally going to assume that graphs are not null. So this probably isn't bothering anybody, but this is a thing that just I want to get out of the way once at the start. So throughout the rest of the course, whenever I'm stating a theorem or whenever I'm in the context of a proof, I'm generally going to be assuming that the graphs in question are not null. And it's because the null graph is sometimes an exception and it's annoying to deal with, so we'll just throw it away at the start. And yeah, that's all I want to say about that one. Next up, we have the complete graph. Actually, in fact, let me just back up and say. So I'll say a graph is complete. A graph, say G, is complete. So a complete graph is a graph that is simple, but subject to that has all possible edges. So it's going to be a simple graph with the feature that for any pair of distinct vertices, there's an edge between them. So any pair of distinct vertices is adjacent. So it's complete if it is simple and all pairs of distinct vertices are adjacent. Okay, so this is a descriptor. A graph can be complete, but it's fairly easy to see that you know up to isomorphism. I mean, there's only going to be one complete graph on n vertices, and we'll give a name to one of them for convenience. So graph is complete if it's simple and all pairs of distinct vertices are adjacent. I want a name for one of these on n vertices. We'll use Kn to denote a complete graph on n vertices. So you could, if you want, insist that Kn have vertex set the integers 1 on up to n or something like this, but we really don't have to worry about that. That's not going to be important for our purposes. I just want it to be some graph that's complete on n vertices. And let me draw you some pictures. So there's K1, and of course I'm drawing this because this is the smallest relevant case. So our graphs, again, we're not going to worry about null graphs. This is K1. This is the complete graph on one vertex. So these definitions, better get that right. There's K2, K3, K4, and so on. So it's perfectly valid to have a complete graph on just one vertex. Then there are no edges. A complete graph on 2 vertices is going to have 1 edge. The complete graph on 3 vertices is a triangle. It's 3 vertices and 3 edges. Right. Okay. So those are the complete graphs. Let's jump ahead. Next up are paths. So a graph is called say G is called a path if so if the vertices can be ordered, put in order, and the edges go in order so that they look like this. So it just looks like a straight line with some vertices on it. So let me say that in a little bit more precise math speak. If the vertices can be ordered v1 up to vn, and edges ordered e1 up to en minus 1, such that what's true, well, what's always going to be true is that the edge ei is going to go between vi and vi plus 1. And I'll just draw that in a picture here. Of course, as usual, I am just telling you straight what's out of the notes. So a slightly more precise write-up of this will appear in the lecture notes. So this is the rule. So in fact, I can just draw this sort of as a generic picture. So it's going to start off with a vertex v1, and then there's e1, and then there's v2, and then there's e2, and then there's v3, and so on, down ending at en minus 1, vn, and vn minus 1. Right, so this looks like a path. It's a pretty good name for the object. A couple of additional descriptors that will be useful here. The ends of this path are the two vertices on the end, v1 comma vn. The length of the path is n minus 1. So the length of the path is the number of edges. If you think about sort of moving along a graph by standing on a vertex, moving along an edge is like a step. You take a step along to another vertex. So that length would be the number of steps you'd need to take to go from one end of your, I'm falling off, from one end of your path to the other. So the length here would be n minus 1. And well, have I gone to? No, that's good. Right, and as we did with complete graphs, I'm going to let Pn denote a path on n vertices. So Pn denotes a path on n vertices. And so here we go. Once again, these definitions make sense right from the start, right from n equals 1. There's P1. P1 makes sense for this. You can have one vertex and no edges, and then you have an ordering of your vertices consisting of just that one vertex, and an ordering of the edges, which is just the empty list, and it satisfies this rule. So this one vertex graph is a path. There's P1. Here's P2. Here's P3, and so on. You can see how this pattern goes. So again, what's going on here, I'm throwing out a couple things. So we have a concept of path. Some graphs are paths, some graphs are not. So for an arbitrary graph, either it is a path if it has this structure, if it looks like one of these things, or not. I'm also giving a name to a family of to a family of paths. So I'm giving a name to a path on one vertex and path on two vertices and so on. And so in light of this, it would be correct to say your graph G is a path if and only if G is isomorphic to P sub n for some positive integer n. Right. Okay. So I don't think there's a lot of complexity or potential confusion there. Let's jump to the next one. That's the very, very similar definition, but a slightly different graph, namely a cycle. So a graph G is a cycle if the vertices of G can be ordered v1 up to vn, and the edges of G ordered e1 up to en. So now you're going to have the same number of vertices and edges in a cycle, such that what's true? Well, they'll draw you the picture first. So here's V1, and here's E1, and here's V2, and here's E2, and here's V2. But it's going to come all the way around. The last edge, En, will go between V1 and Vn. So the rule is that EI has ends Vi and Vi plus 1 for all of the I values from 1 up to n minus 1. And the last edge, En, has ends Vn and V1. Right, so that's what a cycle looks like. So the length of this cycle is n, and as before, I'm going to let I'm going to give a name to a family of these things. We'll let Cn be a cycle on n vertices. Right. So your graph is a cycle if you can put the vertices and edges in order so that you have this incidence pattern. And we have we've now given names to a bunch of these things. So we have C1, C2, C3. Just as we've seen before, these definitions do make sense right from the start. So even for C1, if you have just one vertex and just one edge, this rule works. It will tell you that, so in that case, I'm taking n equals 1, and that will tell you that the edge E1 has to have ends Vn and V1, but your edge has to have ends V1 and V1. That's okay. It can be a loop. So we do have a cycle on one vertex, that's C1. We have a cycle on two vertices. Again, the definition makes sense. If you look at what this means for n equals 2, you're going to have two vertices, you're going to have two edges, both edges, so your two vertices, say V1 and V2, and two edges, E1 and E2, and both E1 and E2 have the same ends. They both have V1 and V2 as ends, so they're parallel edges. That's C2. Here's C3, C4, and so on. Maybe it bears mention here that, again, if I'm giving you a graph that is a path or it's a cycle, the vertices in a graph do not come ordered, right? When I give you a graph, that graph consists of a set of vertices and a set of edges and an incidence relation. If that graph happens to be, say, a path or happens to be a cycle, then there exists a special way of ordering the vertices and exists a special way of ordering the edges that gives you an incidence pattern. But you should be clear that that ordering doesn't come as part of the graph. Like it just exists. You can order them that way if you want, but it's not part of the input graph. Right. I don't think there's too much more to say about this. So we have now 4 families of graphs. We have the null graph, we have paths, and we have cycles. And the null graph, complete graph, paths, and cycles. And we're going to be interested in those graphs, but usually not kind of on their own, but rather as they appear in other graphs. And that's bringing us to our next concept, which is that of a subgraph. So the concept of a subgraph of a graph is a very natural one. I mean, this is a similar thing that you see in lots of other places in mathematics. You have some structure, and there are natural substructures of the same kind contained in it. This is particularly relevant in graph theory. We do a lot of work with subgraphs. The concept is very easy. I give you a big graph G. If you have just some of those vertices and some of the edges, and you use the same incidence on them, well, that's what a subgraph is. And maybe the only thing to sort of warn you about, if you're starting with a big graph and you only want to take some vertices and edges, and then that will give you a subgraph, well, you have to be a little bit careful. If you want to have some edge, say, with ends u and v appearing in your subgraph, well, then your subgraph had better also contain the vertices u and v. So that's really the only restriction. So again, if I'm taking a big graph If I have a big graph G, you can take some subset of those vertices, some subset of those edges, and that will give you a subgraph, so long as you follow the rule that every time you take some edge with ends u and v, you take both u and v as vertices. Now, I'm going to say the same in a slightly more technical form here. If I give you two graphs, or graphs, and I tell you that the vertex set of H is a subset of the vertex set of G, and the edge set of H. Oh, whoops. Better keep writing there. And the edge set of H is a subset of the edge set of G, and incidence in H is same as G, then H is a subgraph of G. And we'll use set theoretic notation to indicate that this is true. We're going to write H subset equal G. So just like you'd write H is like A is a subset of B. So again here, the what's going on is in the graph H, you have some but not necessarily all of the vertices, some but not necessarily all of the edges, but incidence in H has to be the same as it is in G. Right, and so what it means in particular is if you have some edge of your graph G and you want it to appear in H, then both of the ends of that had better appear as well. We will use some more set theoretic notation in this setting. If I give you subgraphs, say H1 and H2 are subgraphs of G, there's a natural subgraph that we can form from the intersection. So H1 intersect H2 is going to be a new subgraph. In fact, let me just write, this is a subgraph of G, and this is going to satisfy the rule that the vertex set of H1 intersect H2 is the intersection of the two vertex sets, and the edge set of H1 intersect H2 is the intersection of the two edge sets. And you can readily verify that that rule does indeed give you a new subgraph. There's an analogous one where we use union instead of intersection, and that follows exactly the rule you would think it would. So if I give you two subgraphs, H1 and H2, you can take the union of their vertex sets and the union of their edge sets and the associated incidence relation coming from G, and that's going to be another subgraph of your original graph. So our subgraphs are pretty flexible objects. We can intersect them and we can union them, and we have other subgraphs. We introduced a little bit earlier in this lecture the concept of, or a family of graphs, some families of graphs, I should say, like the null graph, which we really won't speak of, but complete graphs and cycles and paths. And as I had indicated, complete graphs and cycles and paths aren't that interesting on their own, but they are interesting as structures within a graph. So if you have a subgraph H of a graph G and H is a cycle, we will call H a cycle of G, or we'd call H a path of G, or complete graph, a complete subgraph of G, if that's the type of graph H is. And so although cycles aren't particularly interesting on their own, asking, here's a graph, what is the structure of the cycles appearing in that graph, certainly is. And yeah, so that's a question we'll be looking to down the road. Now it's time for one last bit of terminology and our first theorem. So the degree of a vertex V in a graph G, denoted degree of V, is just the number, that's not very well written, is the number of incident edges where loops count twice. Oh, what am I writing? Counted. I'll just write it twice. So the motivation for this definition is readily apparent from a graph drawing. Say if I draw, use the same graph I always use, more or less. So here's a graph with 5 vertices, A, B, C, D, E. The degree of A is 3. A is incident with 3 ordinary edges. The degree of C is 4. C is incident with 2 ordinary edges and 1 loop edge. So that's 1 plus 1 plus 2 is 4. You can see what degree means in the context of this drawing, right? If you have an ordinary edge with 2 distinct endpoints, then in the drawing, that's a curve from one to the other. So that curve is contributing one little curve sticking out of the vertex. When you have a loop, that we draw as a curve that starts and ends at the same point, and that's contributing 2 little curves starting out of the point. So the degree of the vertex, when you look at that vertex in the drawing, it's sort of the number of curves that start the number of curves that come into that point. Right, so that's the concept of degree. Maybe one quick thing I'll mention here. In some instances in our operations, we are going to have more than one graph in play at the same time. And in fact, frequently it's going to happen even that we have more than one graph in play at the same time, and one vertex might be a vertex of 2 or more graphs simultaneously. In that case, it may be ambiguous to say the degree of the vertex, right? If that's a vertex of more than one graph, then you need to know which one you're talking about. So we're going to use degree sub G of V if the graph G is not clear from context. Right, so the way this works, and this will be the same with other notation that we employ, if the graph under discussion is clear, then there's no reason to write anything more and mess anything up. But if the graph is not clear from context, then we subscript these functions with the name of the graph, so you know which one we're talking about. Great. Okay, so now we're ready for our first theorem. This theorem says for every graph G, when let's say, just to save me from writing V and E. So for every graph G, if you sum up over all vertices the degree of the vertex, you get twice the number of edges of the graph. This is a very simple but really surprisingly useful theorem. It's relating a couple of natural counts that we have. The proof is dead easy. Every time you have an edge, it's contributing 2 to your degree sum, right? If you have an ordinary edge with 2 distinct ends, then it contributes 1 to the degree of one end and 1 to the degree of the other end. If you have a loop, then it's contributing 2 to the degree of that vertex that it's incident with. So every edge contributes 2 to the sum of the degrees, so the sum of the degrees is exactly twice the number of edges. And I don't want to write much about that. Maybe I'll just say proof each edge contributes 2. So as I say, that theorem is it's very simple to prove, but it's a useful identity to have in your head. There's also a corollary of it that is similarly quite obvious and also kind of surprisingly useful. If I add up a bunch of add up a bunch of integers and I get some number that's even, you have to have added an even number of odd ones, right? So this theorem, we're summing up the degrees of the vertices. The degrees are always integers, non-negative integers, in fact, but they're always integers. If they add up to an even number, which they do, that means you must have had an even number of odd ones. So the corollary here is that every graph has an even number of odd degree vertices. So I didn't do great on this. Even number of odd degree vertices. Right, again, this is just the degrees have to sum up to an even number, so you have to have an even number of odd ones. And yeah, as I say, that's it's a direct corollary, and it's all very simple, but this is another one of these theorems that's useful to have in your head and is surprisingly useful in practice. Okay, so that'll end it for this lesson.